And next up, we have Claude-André telling us about the physics of high-redshift bursty galaxies.
Okay, thank you very much. Can you hear me okay? Okay, so this talk is going to be theoretical, and it's going to be primarily about predictions for high-redshift galaxies and the dynamical state of the gas in and around them. So this is work that I've done with a number of collaborators listed on the slide here. Those who are bolded led from the papers from which I will show figures. And many of them will give talks later this week, but I want to highlight a couple which will be directly connected to my presentation. So that's will include a talk tomorrow by Jason Sun, one by Robert Feldman, and on Friday, Andy Marzuski will show results on the mass intelligence relation in these. So many of you are familiar, I think, with the 5 simulations that we use, but I want to briefly summarize the properties. So these are cosmological zoom-in simulations. So they were designed to resolve ISM scale physics in the full cosmological context with a somewhat detailed model for multi-channel stellar feedback. And the videos here are of the formation of a galaxy simulated in this project, which by ZF0 will have a mass similar to the Milky Way. The top panel is gas, color-coded by temperature, and the bottom panel is where the stars are forming, the volume which is being rendered. What you can see is that at high redshift, the cool gas in green is highly clumpy, and it's also highly dynamic. Oftentimes, you see a major radial pulsations in that cool gas. So these are kind of the simulated manifestations of galactic wind powered primarily by supernovae. And it's only at relatively late times, around redshift of 0.7 in this particular simulation, that the gas settles into a long-lived, rotationally supported disk, which is being rendered face on here. And this is a generic phenomenology that we find in fire for systems at this mass scale. In particular, a long-lived thin disk only emerges at relatively late times, or more accurately, when the galaxy and its dark matter halo becomes sufficiently massive. And this is in contrast to what you could see at high redshift when the galaxy was relatively low mass, when it kept blowing itself apart by a bursty stellar feedback. Okay, so we have dozens of simulations like this. So this slide here is now a slightly more quantitative illustration of the phenomenology from the video. So the top panel in black shows a star formation rate in that simulated galaxy in the high redshift regime, from redshift of 4.5 to redshift of 2. And these big spikes in black here represent the fact that the simulated galaxy at high redshift is forming most of its stars in a relatively small number of intense bursts. And typically, each burst of star formation is followed in red by a burst of gas that's outflowing in the circumgalactic medium. The galactic wind powered by supernovae from stars which formed a few million years before. And that corresponds to times where the gas morphology is highly clumpy and, again, highly dynamic. And what I think is somewhat remarkable is that the simulations predict that the same simulated galaxy, by the time it reaches a sufficiently low redshift regime or a sufficiently high mass, settles into a state where the star formation rate is nearly steady. What previously was large-scale outflows reaching far out in the CGM have turned into a much weaker galactic fountain at the disk halo boundary, and that corresponds to times finally where you have these long-lived thin disks, again rendered face on for the gas. These are markable space telescope of some of our galaxies at ZF0. So this is primarily to give you a sense of the level of detail we have in these simulations. Most of them are plotted face on. You have blue light from young stars, attenuated along the line of sight by dust length in some cases. and most of these were selected to be disks for the image. And one of those disks we plotted edge on to show how, even though the progenitor of that Z0 galaxy was a small galaxy that kept exploding at high redshift, it eventually did form a nice thin stellar disk by the time the galaxy became okay, so ZF0 Mark-Hubble Space Telescope images. These are renderings. These were predictions from a few years ago of what some of these galaxies would look like in JWST light. In this case, in the F444 filter from ZF10 simulated galaxies. And you can see already that the stellar light from these galaxies at high redshift was quite different than from the ZF0 Hubble images, much stronger. We now have JWST data that we can compare some of these predictions to. But before I do that, let me stress again that these are simulations which were first published in 2018. There was no tuning to match the JWST observation. Okay? But now that we have the data, we can compare with them. And so one basic metric is these simulations versus the observed rest UV luminosity function, some of the measurements that we heard about this morning. And we did that using a suite of high-redshift Fire 2 simulations. So these are zoom-in simulations that we convolve with the dark matter halo mass function to give you full luminosity function. So this is a reanalysis of the simulations first run 5 years ago by Jason Sun. And the predictions from Fire are the solid maroon curves here, redshift of 8, 10, and 12. And they are compared with observations with the error bars as they were available late last year. And I would say this is an excellent agreement with these JWST luminosity function. And we didn't need to adjust the cosmology or introduce non-standard astrophysical ingredients. This is just what was predicted by the simulation. Now, this is not to say that there isn't anything interesting going on in these high-redshift galaxies. I think it's quite plausible, for instance, that some of them host, an overabundance of very massive stars, for instance. But this is a demonstration that we don't need to introduce those ingredients to match these particular observations. Andy on Friday will show you how these same simulations are an excellent match to the mass metallicity relation measured at the same Okay, so one point that we made in this paper that Jason led is that even though we didn't have to introduce anything special in the simulation to match the UV luminosity function, the burstiness that's predicted by Fire was crucial to achieving this at the bright end. So this is an illustration of this. The reason is simple. It's because the rest UV light that's being measured here is sensitive to the recent star formation rate. So if you have time fluctuating star formation, you're going to have time fluctuating rest UV. And so what this is going to do is that this is going to take galaxies that are not that kind of massive in terms of stellar light, but for short periods of time, occasionally make them kind of rest UV bright because they recently experienced a burst of star formation. And this is going to have an especially large role in boosting the number of galaxies in the high UV luminosity bands, because otherwise these would be populated with only very few galaxies, because massive galaxies are intrinsically rare. You can see that this is about an order of magnitude effect, because while the maroon curve is what we actually predict from Fire, including a self-consistently predicted burstiness, what the blue curve here shows is an artificial calculation on the Fire run, in which we have smoothed in time the star formation history, isolate the effect of burstiness. And then you can see kind of how big of an effect that star formation rate variability is, especially at the highest depth. And one thing to note is that in these simulations, the halo integrated star formation efficiency does not appear to be significantly elevated. So this is a plot that Jason produced of the simulated galaxies that he analyzed from redshift of 8 again to redshift of 12. This is m star over cosmic baryonic fraction times m halo. So this is a fraction of the halo baryonic budget that's been turned into stars as a function of halo mass at these different redshifts. So even for the most massive halos in our analysis, except for a couple exceptions, it's barely more than 10%. And these curves are very similar actually to an extrapolation of what the m star m halo relation is at lower redshift. Okay, now in the rest of my presentation, I want to do a deeper dive into this transition from bursty star formation to a steady star formation and the emergence of its disk, but with a focus on the dynamical properties of the gas in the high redshift regime, which we suspect is kind of closely related to the burstiness and important to explain the star formation efficiency. So these slides are from a paper that my former student Alex Gervich led for his PhD thesis. This is a case study of 3 simulated galaxies. These are their names, which by Z of 0 will have a mass similar to the Milky Way. And what this first slide here shows is how in any given run, we can identify relatively precisely when is it that the star formation rate ceases to be bursty. And it's because that occurs relatively abruptly relative to a cosmological time scale. So the 2 panels here are 2 different measures of star formation rate variability. So the top panel is star formation rate averaged over 2 different time scales, so the ratio of the 2. And the bottom panel is sigma, the standard deviation of the log of the star formation rate. Okay? And so, for example, if you look at the standard deviation of the log of the star formation rate, you can see that it drops by about an order of magnitude less than 1 gigayear as we transition from the bursty era to the steady phase. Okay, and each kind of age of the universe at which a galaxy stops being bursty, we label T bursty. So this is the time at the end of bursty star formation. And in this plot, as on upcoming slides, we've kind of shifted all the simulations in time and plotted the time histories relative to delta T. So age of the universe minus the time at which the formation rate becomes steady. Okay, so a key result from that paper is that the end of bursty star formation correlates very tightly with the emergence of a thin galactic disk. And I think this is something you're going to hear more about on Wednesday from James and others. So the 3 panels here are, as a function of delta T, different metrics of diskiness. For the gas, solid lines, all the stars, long dashes, and only the young stars, the dotted line. The top panel is the geometric aspect ratio. So values of order unity means geometrically big. Small values mean disky. The middle panel is Jz over Jc. So J, specific angular momentum. Z means along the kind of mean axis of rotation. And Jc is specific angular momentum for resolution elements that would be hypothetically on purely circular orbit. This is a metric which is of order 0 on average when you have kind of random motion, but which becomes unity when all your angular momentum vectors become aligned with each other. And the bottom panel is a more observationally motivated metrics of diskiness or rotational support. So this is V phi. So rotational velocity divided by sigma velocity dispersion in the H1 gas. What you can see is that in each one of these metrics, if you focus especially on the gas or the young stars, the diskiness increases with time and becomes a very coherent right around the end of bursty star formation. So this is a signature that your gas has settled into a very thin disk, and from that point on, it's forming its stars in a thin disk. If you look closely, you'll notice that while the end of bursty star formation correlates very tightly with the emergence of a thin disk, there is some gradual increase in rotational support that begins somewhat before, and we interpret that as a gradual formation at earlier time of what would be later observationally identified as theorelic thick stellar disk. Okay. Now, I want to focus a little bit more on the properties of the gas in and around those galaxies. So this is for a particular example galaxy, a decomposition of the energy in the gas. We're focusing on the inner halo, kind of within the galaxy, into orthogonal kinetic components. So this is in the radial direction, in the azimuthal direction, and along the axis of rotation, and thermal energy. And what you can see is that in the bursty phase on the left, you basically, while you have large fluctuations in time in all these energy components, have a rough equipartition between the different kinetic energy components and the thermal energy components. So this is a signature of the dispersion-dominated physical state of the gas. But around the end of bursty star formation, nearly all the energy goes into the rotational kinetic energy component in yellow. That's when you form a coherent, long-lived disk in the steady state. Okay, next we can look at how big these energy components are relative to the gravitational binding energy on the scale where they are measured. So this is with the same color scheme as on the previous slide for the kinetic energy component, the thermal energy component in red, and the sum of the two in black, kind of the total energy in the gas. This is relative to the gravitational binding energy. So what you can see that in the bursty phase, while again you have large fluctuations, an important feature is that this total energy is often above the gravitational binding energy, and it's especially the case at the earliest time or at the highest redshift. So this is a signature of the fact that in the highest redshift simulated galaxies in the bursty phase, this gas can get quite far out into the halo. Dispersion-dominated motion really leave the galaxy and expand into the halo. In contrast to the situation in the steady state, when again most of the gas is in the kind of thin configuration dominated by rotation. Okay, so next we're going to look at this as a function of spatial scale. So notice here now the axis is radius as a fraction of the virial radius. So from roughly 1% of the virial radius, that would be within what you would normally call the galaxy, out to 1 virial radius, kind of the outer CGN. The top panel is kind of the fraction of the total energy that's in the different kinetic and thermal components relative to the total at the time while the galaxy is still highly bursty. And the bottom panel is similar quantities, but in the steady phase, once the bursty star formation has ended. And what you can see is that in the bursty phase, there's basically no way to tell where the galaxy ends and when the circumgalactic medium begins. This is a map of gas temperature in the halo at that time, and basically it's a complex dynamic multi-phase mixture of gas from the middle of the halo out to the virial radius with no clear boundary between where the ISM ends and where the circumgalactic medium begins. Okay, and this is in contrast to what we find once you have a steady disk, where you can kind of see by eye where you might call the end of the galaxy and the beginning of the circumgalactic medium. You could associate that with kind of the edge of the rotationally supported disk, and you can also see visually in that case that this kinematically cold disk is kind of thermodynamically distinct surrounding the circumgalaxy. So this is a schematic illustration of the kind of physical picture that I've kind of illustrated from the first simulation. So you have an early bursty phase that dominates at low masses. In that phase, kind of the ISM halo a kind of combined system is a complex, dynamic, turbulent-like multi-phase mixture, really extending out to the circumgalactic medium, and that eventually evolves in the steady phase into a different kind of system in which you have a cold rotationally supported disk embedded in a hot CGM, which you can kind of clearly distinguish from the central galaxy. So one of the key points that I'm trying to make here is that the common picture where you have a galaxy and outside of the galaxy you have the CGM, this may not be a good way to think about these high-redshift bursty galaxies. It's more like a large-scale, highly dynamic system, at least when viewed from the gas dynamic perspective. So some potential implications. So many modeling approaches, including analytic models, analytic models, and more idealized simulations, assume kind of in the initial conditions that galaxies can be well modeled by equilibrium disk conditions. And I have done this in many of my own papers, and it is a reasonable set of assumptions in some regimes. But this does not appear to be a reasonable set of assumptions for galaxies in the bursty phase, and this may have implications for how we think about how galaxies regulate the star formation, say by stellar feedback, or how galactic winds are launched. And an idea, which you'll hear more about from Jason tomorrow, is that perhaps a fruitful way to think about these high-redshift galaxy halos is using an approach that is inspired by turbulence. So that would be a picture in which the halo as a whole is quasi-turbulent and in which star-forming clumps that you may associate with kind of galaxies in the middle correspond to density peaks in a kind of a complex flow. So this would be an analogy to how turbulence is often used to understand how star formation occurs deep inside molecular clouds, but kind of generalized to larger scales. And this is kind of my last slide, leave you with a visual impression of this. So this is a rendering of the gas distribution on halo scale from a fire galaxy formation simulation compared with a rendering of the gas deep into a turbulent molecular cloud from the fire project. And as I mentioned, Jason tomorrow will expand on how kind of this turbulent picture on halo scale may be useful in understanding the relatively modest star formation efficiencies that we predict in fire, even in the very dense kind of integrated conditions of high-redshift.
Claude-André. Lots of questions. Some of you might have.
Quick question. Do you consider the evolution of galaxy radii?
It is subconsistently, so there's subconsistent galaxy radius evolution. So the galaxies are much more compact, high redshift. I don't think we have a paper that goes out to very high redshift. Jason, can you correct me? Maybe one of the early papers by Zheng Shengma. If we have papers at low redshift? Yeah, so the galactic radii have been plotted in various papers. Typically, it hasn't been a paper in which the title is Evolution of Galaxy Sizes. But definitely the galaxies, they are much more compact at high redshift in these simulations in a way that I think is broadly consistent with the observations, but we have not yet done a detailed quantitative.
Thank you very much for this. I wonder, can you quantify in any meaningful way what fraction of these trends that you're demonstrating so beautifully are due to halo mass versus redshift?
Yes. It appears to be primarily halo mass, and they correlate very quickly.
I guess I'm saying
the transitions occur at the halo mass that you could call the golden halo mass. It correlates very tightly with the realization of the inner circumgalaxy.
So if you were to repeat this series of experiments with, instead of Milky Way mass halos that were at redshift 0, 10 to the 13 or 10 to the 13.5, would this look basically the same, or would you really
I believe it would look qualitatively the same, but the transition would occur when your halo becomes of order 10 to 12 solar mass.
Even if that occurs at high redshift, I mean, yeah, okay.
Yes. So so for example, in Jonathan Stern's 2021 paper, we looked at kind of all the mass scales we had in the simulation.
So, Claude-André, this is very beautiful work, and it probably has something to do with the real universe, but you haven't included any AGNs. What effect would AGN inclusion have had on the various things that you've discussed? This may be something that we want to talk about in the discussion.
That's a good question. So all of these simulations neglected AGN feedback. It's intentional because while in some of our newer simulations we do have black hole growth and AGN feedback, the way we model AGN is highly kind of dependent on what the assumptions that we put in, which is a situation that's different from the stellar feedback, where it's much more connected to kind of a standard set of stellar population evolution models. And so we'll have to see. It's a model. It's not the real universe, but a plausible hypothesis for why what I just showed you would not be completely changed by the inclusion of AGN is that in our own simulations, as in many others, intense black hole growth seems to only occur after you have kind of stabilized the gas reservoir around the galactic nucleus. That is, after you have kind of entered this steady phase. And so if this holds up in the real universe, kind of the picture would be black holes are there, but in the bursty phase they don't grow very much. And by the time they start growing intensely, then you have very strong AGN feedback, kind of starting at the L-star mass scale. You kind of pass the transitions which I've emphasized in my talk. And then that would be important for like the later evolution of the galaxy quenching, etc. But it wouldn't kind of drastically modify the physical picture up to the point where.
So unfortunately, we're going to have to move on. But the good thing is Claude-André is going to be back on the mic in 15 minutes. If you're planning on asking about cosmic rays, magnetic fields, thermal conduction, you can grill him about that then. So next up, we have